And again, welcome to today's webinar, Build a Scalable Search Engine with the new Amazon CloudSearch. Our presenter is John Hetler, Solution Architect with Amazon Web Services. Today, we also invite Praveen Masukuma to join us later in the Q&A session. Praveen is the Senior Product Manager with AWS. John, you have the floor.
Thanks, Bowen, and good morning, everybody. Thanks for coming to the webinar. Today we're talking about how to build a search engine in the cloud with Amazon CloudSearch. Got a ton of material, so let's go ahead and dive right in. Amazon CloudSearch is an AWS service. We've been out for 2 years now, and we have recently upgraded our service and brought out a ton of new features. We're going to cover all of those features today in some detail and how to use them. But before we get into that, we're going to talk about search engines and search as an application and what do search engines do and how do they accomplish it. So just to give us a little grounding and a background in the search application, and then we can look at Amazon CloudSearch and how CloudSearch solves those problems, and then specifically some of the new features and other things that we've added. So when we have an information need, when we go to the web to buy things, when we want to figure something out, more and more we're going to a search engine to do that. More and more the search box is popping up and is enabling us to get from a goal that we have in finding information or finding products or finding services to the data that represents those services. And as we look at the IT landscape, we see that more and more there are devices in the world that are collecting data. More and more data is coming to the fore, and search engines are an integral part in getting us to the data that we're interested in for solving our goals. Well, how do they do that? So I've taken a page from IMDb, that's the movie database online, and if we look at it, what we have here is a representation of a single movie, Iron Man. This, in a search engine, would be structured as a single document. This document is actually a composite structure, so there are a number of different parts to it. For instance, we have a title, we have a description, we have directors, writers, stars, we have some rating data that came from either users of the site, or in this case there's a Metacritic site, there's a Metascore, there are reviews. All of this information is part of, as well, we have related content like videos or photos, again, critic reviews. All of this content relates to this particular piece of this particular movie. And we structure all of that into a single object that we call a document. The search document is really the core of the search application. It's the data structured together, and then queries retrieve those documents as search results. Internally, we represent a document in terms of fields and values. So every search document has an ID, and this ID is unique within the search engine and identifies this particular target, this document. Then we have our set of pieces of information that we've collected together about this document. So we have a title, description, director, actors, etc. All of this information comes together and is structured as essentially fields and values for the search engine. As the search engine takes in this information, it processes each of these fields in different ways depending on usually a configuration that we set up that tells the search engine what should it do. Some of the data types that we have are text, and text fields, as we'll see in a second, are processed so that individual words from that piece of text can match user queries. We also have literal fields. Literal fields are not text processed, but these are strings that match exactly. So those are typically used for the UI portions of the search experience, where the application is in control of the the text that's running against the search engine for the matching. We have dates. These are processed as dates and allow us to do things like sort things by freshness or search within date ranges. We have double values. These give us, again, the ability to search across ranges. We have signed integers, again, for searching across ranges, also useful in ranking, as we'll see. And we also have geotypes. These allow us to either search geographically or, especially in a mobile context, they allow us to find things that are close to a particular user. When we process text for searching, we want to make sure that the text itself is in a form that allows for the best possible matching experience. So in particular, we want to cut up the text into individual words. And we do this in a process called parsing or tokenization. Usually white space based, although punctuation can come in there as well to add tokens. This is the process of splitting out basically the atoms that we're going to use for matching against what users type in a search box. Because we typically want to match more rather than less, we want to downcase things. So when we have a string like Tony Stark, which is capitalized, we'd like that to match when the user types Tony with a capital letter or without a capital letter. So we downcase everything as we bring it into the search engine. We run through a process called stemming. This brings words to their common stems. In this case, we can see industrialist brought to its stem industrial. This means, again, if users type industrial or industrialist, we want them to be able to match this particular piece of text. We also remove what we call stop words. These are words that are very common and provide little value in terms of matching, like the a or an. These words would match in many, many documents and won't provide a good filtering or sorting criterion for bringing the best matches. Finally, we frequently will add synonyms so that when users type, for instance, I don't have a good example on the tip of my tongue. Synonyms expand the range of matches that users can get with their terms. Once we've cut up all of our text, we build what's called an index. An index takes a particular word that's been somewhere in our set of documents and generates the list of IDs in which that word occurs. So in this case, I have the examples of iron and man. The term iron appears in a number of different documents, and we create the list of those documents, including the man in the iron mask, Iron Man 2, Iron Man, etc. And we store this in our index structure. Similarly for man, and similarly for every term that comes in our source set of documents. This allows us to do matching in a very efficient manner. So we take the terms that the user has typed, look them up in our index, and get the list of the document IDs for which those match. Now, I've expanded the document IDs out here to titles so it's easier to follow. But essentially what we end up with is a list of matches for each of the terms that have come in the query. We then apply the logic of the query so that, in this case, it's an intersection. We apply the logic of the query to find the intersection, in this case, of the document IDs that are matching for both terms. This gives us our final match, which takes into account, again, all of the words that the user has typed, and if there are other elements of the query and other Boolean expressions in the query, all of that will boil down to a set of document IDs that match for this particular query. But of course, search engines don't just bring things that match. The point of a search engine is to bring the best information, the best matches at the top. Once we have our set of actually matching documents, we then compute a score for each of those documents so that we can sort them and bring the best documents first. The typical scoring criterion is called TF-IDF, and TF-IDF is a strictly text-based scoring mechanism that looks at, for each of the words the user has typed, how common are those words, and how often do they appear in each of the matching documents. If a user types a relatively rare term that occurs often in a particular matching document, that document receives a high score. If a user types a very common term, or it's a term that does not occur very often in the matching document, that document would get a lower score. Strictly text-wise, this gives us a measure of the match between the user's query and a particular document. However, there are many additional criteria that allow us to discriminate between very similar seeming documents. These are usually added in after the fact or along with the TF-IDF score. And some of these include a measure of the document value. So if we have users who have given ratings to movies, then we want to include the rating in the overall score for a particular document. We'd like to bring better movies to the top. We frequently roll in user behavior. So if we know that for a particular query, users or many users have clicked on a particular document, we'd like to bring that into the score. And another common one is freshness, so that newer things, like newer movies, would, generally speaking, be of more relevance to a user. So we want to bring those to the top. We roll all of this into a score function and then sort the results. The best scoring document is the one that we bring to the top. So just in summary in this section, and looking at what does search do, search is really a way of taking my goals and bringing the best possible matches for those goals. It's a pathway for me to get into a big data set. Documents within that data set are the search targets, and we gather the information that's pertinent to those documents into a structured format and send that to the search engine as the core of the search experience. We build an index in a search engine to provide the basis of matching, and then we use relevance to look at all of the matching documents and bring the best ones up to the top. So we're going to move into talking a little bit about Amazon CloudSearch. And starting off with, okay, so this search stuff is great, and how do I go about doing it? Well, there are a number of different ways that you can add search to an application. First of all, you can build your own. And we do see this quite a bit, especially because within databases, we have a search capability. Generally brought with the moral equivalent of this is like that, so direct text-to-text matching, or some of the open source databases do have a more extended search capability. What we find there, though, is that where a search engine really excels is in the text processing that I outlined above, as well as in the generation of relevance values and the scoring that I've mentioned above. So search really differentiates from a database in that it provides enhanced text capabilities and enhanced scoring capabilities. You can also build your own custom search engine. This is a fairly difficult proposition, and if the core mission of your application is search, it may be relevant, but it's quite a task to take on to build your own search engine. There are open source alternatives as well. Two of the main alternatives are listed there. There's Apache Solr and Elasticsearch. You can definitely go that route. What we typically find there is that those methods have a lot of management and other overhead that makes them a little bit less attractive. And then finally, there are some legacy search implementations, FAST, Autonomy, and DECA. These are large-scale solutions that you can employ to add search to your application. Now, as I've mentioned, there are definitely challenges with building your own search service. First of all, it's very complex. As I mentioned, to build an actual search engine takes many person-years of effort and requires upgrades and maintenance and all of the other things that you have to do. Even in the open source realm, maintaining and configuring and getting your search engine scaled up and functioning within the context of your application is a difficult proposition, not to mention that there's often an upfront expense which is difficult to manage. If you're not deploying this on the cloud, you have to rack servers, you have to get all of the infrastructure in place. In either case, if you're building it, you need to build it as code or get the open source software downloaded, set up, all of that. All of this means that there's a long time to market, and fundamentally, this is undifferentiated work that doesn't particularly relate to your application or your core competencies that you really want to be working on to make your application better. Amazon CloudSearch, as I mentioned, is an AWS service, and as such, we have many of the benefits that AWS brings in other realms. So CloudSearch itself is easy to set up and operate, as we'll see in a second. You don't have to rack hardware up front. You pay as you go. CloudSearch is automatically scaling, so it fits itself to your need. There's no need to guess capacity. I've worked in a number of contexts building search engines, and in all of those cases, we spent an inordinate amount of time trying to guess our capacity needs for things like holiday seasons, daily spikes. All of that is difficult to do, and again, undifferentiated. You don't need to guess the capacity with CloudSearch. You can experiment fast. It's very easy to get started, very easy to use, and you can go global in minutes. CloudSearch is now deployed in all of the AWS regions, minus GovCloud, and you can push out your search application to all of those regions very simply. Okay, we're going to transition into talking about CloudSearch and looking at the features that we've brought out recently. With CloudSearch, you start with what we call a search domain. A search domain wraps all of the software and hardware needed to run a search engine in the cloud. You click on the Create Your First Search Domain button, or if you've already got some domains created, there is a Create Your Domain button. This is our AWS console that I'm showing here. CloudSearch will answer back with a wizard that walks you through just a few steps. You name your domain. You put in a preliminary configuration. You set up some access control and click Confirm. Just a few steps, and within about 10 minutes, you'll have a search engine deployed and ready for you in the cloud. Once you've created your search domain, you need to upload some data to that domain. Again, we have some help inside the console. Here you can see in the upper left, you can upload documents through the console and send them to your CloudSearch domain. When you're uploading documents through the console, again, you can use local files on your disk. You can point at S3. You can point at DynamoDB, or you can use some canned data. A couple of things to say about this. The console itself is not really meant to be a heavy-duty data channel. So we've got this wizard in the console that helps you out just to get started and try things. In normal operation, what you would do is you would build a script that pulls data out of however many sources there are for that data. As we saw in the compound document, there may be multiple different sources. All of that data is put together into a single search document and then sent to your search domain via HTTP. The other thing to mention here is that we have not only the console, we also have a command line interface that makes this process simpler, posting documents to your domain. And we also have direct to API. You can directly talk to your search domain over HTTP. Having a little bit of a deeper look at the upload experience, your search domain provides for you two endpoints. The first endpoint is a document endpoint. This is, again, provided through DNS. It's stable through all of the life of your domain, including the scaling up. and provides you with a place to post your documents. I've got an example post here, and you can see we have the header, just the type and where the thing is going, and then we have the document itself. And the document is, again, what you post to CloudSearch is a batch. Within that batch, you have some documents. Here we have an add and a delete, and each document has an ID, and the add has a set of fields that will be taken in and processed according to the configuration on the domain. So what I'm showing here is a typical search result experience, and we're going to walk through this in some detail to understand how this UI comes to be, how you interact with CloudSearch to bring this kind of search experience. And the first thing we'll look at is simple queries. With simple queries, we're just taking the text that the user has typed, and we're sending that off to CloudSearch to retrieve a set of matches for that search result. As I mentioned, your search domain provides you with two endpoints. The first is the document endpoint. The second is the search endpoint. In this case, we send a GET request to our search endpoint. We use the API version and then the search resource. We use Q equals to run a simple search against all of the text fields in the domain. Thinking back against the fields that we have actors, directors, we have an image URL, a plot, and a title. These are all configured as text fields. This query goes against all of those fields to pull up a set of matches, which comes back as a search result looking like this. In our search result, we have minimally the ID for each of the documents. In this case, I've included some highlights. But we don't want to have only simple searches. We do want to also support more complex queries that take into account things like refinements that the user has added through the faceting interface, as well as other things perhaps that the application has added through the path the user has taken to get to this particular page. So if we want to search for Iron Man and we want to limit the search to movies, sci-fi, fantasy, 2008 to 2010 with actor Downey, we can write that query in the following way. And I've elided the search endpoint here. We just search with Q equals again, and we use a prefix notation for expressions. So in this case, we're taking the intersection, the AND, of the term iron, genre sci-fi fantasy, actors Downey. Here we have an example of an integer range. We can search between 2008 and 2010. And again, within the category movies, we specify a different parser in this case. We're going to use a structured parser that's going to take that query, parse it up, and generate all of the matches according to the index. And then we want to actually add an option here where we're going to weight our fields so that our title weight counts twice as much in the scoring as the plot. If we look at that result, here again, we see the ID, and we've retrieved some fields in this case. Iron Man and Iron Man 2 come back. Often, as I mentioned, our users will want to drill into the result set and will want to use what we call facets to allow the users to narrow their query to particular things. In this case, we have a simple facet here called genres, and we're displaying for the matches for this query how many of those had this value for that field. So in the genre field, 62 of the results that matched Iron Man had action as one of the values for their genre field. 25 were sci-fi and fantasy, 2 were comedy, etc. Typically, we'll see this in the UI this way, where users can then click on those as links, and we'll generate a query in the back end to add that component to the query. So if we look at faceting in a little bit of detail, The first thing is within our configuration, we have to enable faceting for that field. I've got a really small snapshot console here. This is showing the configuration that I can run or that I can add for this field. And you'll see my field name is genres. I have a search, a facet, and a return option. I've set facet to be on so that facet counts will be computed for this field, and they're available for querying. Then, within the query itself, I search for the text, Iron Man, and I ask for genres on the facet, or I ask for the facet values for genres. In the result, I'll see, again, I have my search status and hits, and then at the end of my search results, I have the facet values, and you can see these map almost one-to-one with the UI. One of the most important things, as I mentioned, that search engines do is they provide an adjustable ranking over the matches for a particular query. And we want to make sure that we are able to build not only a basic text-to-text relevance score, we also want to be able to add in other components. CloudSearch exposes this functionality by what we call expressions. In CloudSearch, I can build an expression as an algebraic function, and I can use the TF-IDF value. This is the baseline ranking that we get out of the box. I can also, again, generate an algebraic expression that includes both the TF-IDF score and other fields, the values of other fields. So if I want to add something like freshness, I can use either a year field or a date field and add a function that takes either directly subtracts the difference between the latest and the value for each of the documents, or I can use an exponential function that allows me to do an exponential decay across the age of the document. And I can use this to bring a different value to the score, bring that freshness into the score. Same thing with popularity. I can add that directly into the score. I can use powers, exponents, trigonometric functions. I have a distance function available to me. If I'm doing a mobile application, I can then use the distance for a particular document, and I can score based on the location of the user with respect to the document. And I can do this in a static way, where I can define these functions on the domain, or I can do it in a dynamic way, generating a function expression and attaching it to the query so that I can do customization either on a per user basis or per query basis. Finally, another part of the search experience is highlighting. Highlighting shows a user what part of a document has matched their query. In this case, if I query for Iron Man, I could see here in this description, in this plot summary, that the word Iron Man occurs. And in my UI, I'd like to display that in a way that calls it out to the user. So then when the user looks at this, they can say, okay, yes, Iron Man matched this particular plot. For this example, of course, all of the titles also match, so those could be highlighted as well. Depending on the application, you would highlight different elements to make sure that the user understood that that was where their query had matched. We can accomplish highlighting with CloudSearch. Again, looking at our configuration panel, you can see here I have a plot field, and I have my option for highlight is checked. This is really one of the benefits that CloudSearch brings. As we look at the open source alternatives, highlighting in particular is one where there's many, many different ways to do highlighting. Configuring it, setting it up, getting it to function correctly is a chore. And with CloudSearch, what we've provided is a really simple single checkbox that tells the search engine, I would like to retrieve highlights from this field. That's all you have to do. Along with the query, I'm searching for Iron Man, and I'm asking for a highlight in the plot field in a text format. We have several controls that we expose. You can get an HTML response. You have controls over the number of items within each snippet that are highlighted, and we also allow you control over the pre and post tag for that highlight. In the search result, again, I have my status line, my set of hits, and within each hit, I see I have a highlights section, and the field name is plot, and here you can see the Iron Man is given the default star to indicate that in the UI this should be emphasized in some way. So it's really just that simple to pull highlights out of CloudSearch domain. Another UI experience for search that's important is what we call autocomplete, or in other terms, search suggestions. This is an experience where as the user is typing, the UI will generate a drop box that contains a list of possible completions for the terms or the characters the user has already typed. This is extremely useful in a mobile context where keyboards are small, people make errors. It's really nice to be able to display a set of potential completions so that users don't have to go through the process of completing out the words. In this case, I've typed IR, and I get some suggestions, Iron Man 3 and Jeremy Irons, Max Irons, a number of different suggestions. For CloudSearch, what I do is I configure what we call a suggester, and within CloudSearch, there's a simple wizard that walks me through this. My suggester is based on a particular field in my source documents. I can configure up to 10 suggesters per domain, and the suggester itself takes the text of that field and provides that as a potential for completion. There are some options I can set. I can add an expression that will be applied for sorting the possible suggestions, and then I can also turn on different levels of fuzzy matching. So this gives me some criteria. Do I want an exact match here, or do I want a little bit of looseness in how well the first characters have to match? In order to get my suggestions, I again go to my search endpoint, and I use my suggest resource, and I use a very similar structure. I say Q equals with the characters the user has typed already. I specify which suggester I'd like to use for this suggestion, and CloudSearch responds with a response of very similar format, where I have a status and then the set of suggestions. And here you can see I have Iron Man 3 and Iron Man. My score there is 0 because I don't have a sort expression, and I get also the set of document IDs that match that particular suggestion. This allows me to go and either retrieve information for those to make a more detailed UI than just the characters, or I could just display the textual suggestions as is. Some of the management and other features that we've recently come out with make, again, deploying and operating your search domain a lot easier. We've recently added availability options, and this allows you to, with a single click here on the multi-AZ button, deploy your search domain across 2 different AWS Amazon availability zones. This gives you a high availability solution, and again, this is a task that takes quite a bit of effort if you're in a do-it-yourself kind of context. With CloudSearch, you simply click the Turn Multi-AZ on, and CloudSearch in the back deploys your domain equally across 2 different availability zones. Search traffic will go to both of those zones, and the upload traffic will get distributed to each of the zones so that each zone remains in sync. As well, there's a failover, which is not so much a failover because both zones are hot. So if one zone should drop out for any reason, you would have the other zone remaining up to handle queries. Just as a cost detail, this will actually approximately double the cost of the domain. However, in a production context, that tends to be worth it for the peace of mind of knowing that you have a high availability search solution in place. Another feature that we've released that makes CloudSearch easier to operate is a scaling options feature. This allows you at domain creation time or any time in the lifetime of the domain to set a minimum instance type and replication count. CloudSearch, as I've mentioned, is an automatic scaling solution. So as you're sending documents to CloudSearch, CloudSearch is deploying those documents to an index, and that index is getting deployed based on its size to a particular instance type. As you scale up the amount of data, CloudSearch will scale up the instances to hold that data. And in fact, if you exceed the maximum instance size, which is the M22X large, CloudSearch will partition that data, deploy that partitioned index to multiple hosts, and serve traffic out of that index automatically. So CloudSearch itself scales up in instance type as you send in more data to your document endpoint. Additionally, as you send in traffic to your search endpoint, CloudSearch will add replicas of each of your partitions. If it's one or many, it will add replicas of those partitions to serve that additional traffic. It will add and then also remove instances or replicas as needed as data grows and shrinks and traffic grows and shrinks. So it's an elastic solution that really takes all of the heavy lifting of figuring out how to deploy across multiple nodes within a search cluster and does it for you. We've exposed this feature to enable our customers to scale up their own search domain in a couple of different situations where that comes up. And the first of those is on domain creation. If you have a large amount of data, then starting on a small instance does not provide the smoothest warm-up experience. So for large amounts of data in the tens of gigabytes range, you would start on a larger instance, extra large or double extra large. This provides a bigger pipe for you to push the data in more quickly at the beginning. For replication, we've provided this so that if you have a known traffic spike, you can pre-warm your CloudSearch domain to handle that spike and not have to wait for the automatic scaling to kick in. This would be useful in a context, for instance, a news agency. If you know that you're pushing out a big story and people will be coming to the site and doing a lot of searching, you can bump up your replication count and handle that without, again, waiting for the automatic scaling to kick in. We've also released some integration with IAM, and this at the moment is for the configuration API only. Your configuration API allows control over creating and deleting domains and doing other operational tasks. With CloudSearch, you would create an IAM policy, and we've exposed the ability to control access to particular IAM roles on a per domain, per region, per action basis. So you have a very fine-grained control over which IAM roles can perform which administrative functions. So in closing, as we see the amount of data grow in the world, and as we look at different applications, more and more we're turning to search to get us from our intended goal to the data or functionality that will allow us to solve that goal. So search itself is really becoming ubiquitous and one of the first things that we want to turn to when we want to find something, obviously. CloudSearch, fully managed service that provides automatic scale, easy operation, easy integration, cost-effective search, and you can get the powerful features that you find in most open source search engines along with value-add AWS features, on-demand pricing, automatic scaling, high availability, global availability out of the box. So we're going to turn to Q&A. And as Bowen mentioned at the beginning of the session, you can find a question pod on your screen. If you have questions, please send them out. And I'm going to ask Praveen to help me out here by sending those questions my way.
Great. Thank you, John. So thanks, audience, for submitting great questions. As our presenter is reviewing the questions, let's launch today's poll. The first poll is, overall, how satisfied are you with today's webinar? Please take a moment and cast your vote. Okay, great. The next question, what is the topic you want to learn next? Again, please take a moment to let us know what the topic you'd like to learn from AWS Webinar Program team. Okay, we'll give audience a couple more seconds. Okay, the last question, how effective was the presenter in communicating today's content? Great, thank you for your feedback. Now we'll start a Q&A.
All right, thank you, Bowen. And as John and Bowen mentioned, please do continue to submit questions on the question panel on your screen, and we will answer as many as we can in the next few minutes here. So, John, the first question we have is around the geospatial feature. Can you talk a little bit more about how that works with CloudSearch and how users can set that up?
Yeah, absolutely. Within the search document, you would provide a latitude, longitude. Within a single field, there's a syntax there. You provide it as a string pair separated by a comma. And then for the configuration, we have a lat/lon type. So you can configure that field as a lat/lon field. And then querying that field, you can either use an integer range. So you can use a lat/lon range, basically, to do a bounding box search and providing the geographic top left and bottom right corners of a rectangle and search within that to locate documents that match anywhere within that rectangle. So in the matching phase, you can use filtering to filter out documents that fall in or out of a particular geographic range. For sorting, we provide the Haversine distance function, and this again operates on a lat/lon field and would compare the lat/lon that you would pass in as part of the query, so the user's current latitude and longitude, and would compute the distance to each of the documents based on that document's lat/lon field and sort the results. You can have it sort the results based on that distance value. So you would sort ascending. The closest values would be the documents that match that were closest to that particular query or that particular user.
Perfect. Thank you, John. The next question we have is, how quickly are uploaded documents available for searching with CloudSearch?
We don't have a tight SLA on document updates. What we find in practice is that documents on average are available in about 10 seconds, and we would see that grow out depending on the update load at any particular time and depending on the ratio of the amount of uploaded documents to the size of the domain. That can grow out to 5 minutes or 10 minutes. So somewhere in there, again, average times we see are in the 10-second or so range.
Okay. Next question. What is the largest index size that CloudSearch can support?
So we are currently supporting a 5 terabyte index, and we feel like that is in the range of the largest amount of source data that we'd like to support at this time. As we go forward, we're going to be lifting the cap on that and working to make that limit much larger. However, for now, 5 terabytes or so would be a maximum that we would, out of the box, try to support.
Okay. Next question. Can you specify multiple suggesters when using the new suggestion feature?
So with CloudSearch, you can configure, again, as I mentioned, up to 10 suggesters. Within a particular suggester query, I believe you can only specify a single suggester for that suggester query, but there's nothing stopping you from running parallel queries that would pull suggestions from different fields, and then at a UI or application level, you could decide how to mix or blend those.
Okay, a similar follow-up question. Can multiple highlight fields be specified in a single query?
Yeah, within a single query, you can specify as many fields as you have set up to be highlighted. Within the search response, as we saw, there's a highlights section, and that section would contain the field name and highlight for each of the fields that you requested in the query. So you can specify, again, as many highlight fields as you have set up.
Got it. The next question is about language support. CloudSearch handles queries in Spanish. How does it handle accent marks over certain letters which may or may not be included in queries by users?
Excellent question. So one of the things that we have come out with this new version of CloudSearch is native support for various languages. And we have about 33, I think, at last count languages that we are supporting, from Arabic through Turkish, including some of the more difficult to handle languages like Chinese, Japanese, Korean, German, the ones that require a more complex text segmentation scheme. Within those languages, again, the treatment is at a native level. CloudSearch supports the full Unicode character set through UTF-8, and so you can absolutely send in documents that contain accented characters as well. We support that at a query level, and then for matching, if we would support that in a native language level. So if you sent in Spanish text and treated it as English, we would do accent removal. But if you treated it as Spanish, we would handle that as Spanish language. So the accents, I believe, should match.
Okay, perfect. The next question is regarding one of the examples you showed in your presentation, John. In the faceted search example, how was the hierarchy of counts achieved in the right side of the screen?
Yeah, excellent question. A little bit more detail on hierarchical faceting. So the way we accomplish this with CloudSearch is to provide multiple fields at each level of the hierarchy. I'm just going to back the slideshow up here, or I'm going to jump around in it, just so we can have that up on the screen. So what you'll see here is we have an Oscars field, and that has awards at the second level and nominations. And then below that we have actors, actresses, supporting actors, and supporting actresses for the awards field. So the way to accomplish this within the search engine is to create 3 fields, one for each level of the tree, and then the values for those fields you would provide as a path. So for instance, for the movie that contains Daniel Day-Lewis, you would have a level 1 field that would contain just Oscars, and actually I've got it wrong. You contain a level 1 that would be just awards, and then a level 2 that would be awards and then some separator like a slash, so awards/actor, and then a level 3 field that would contain awards/actor/Daniel Day-Lewis. When you make a query you retrieve facets at all 3 levels of the tree. So if I search for, not Iron Man, but if I search for something like Lincoln that actually had Daniel Day-Lewis in it, I would get, at level 1, I would have at least 1 count against awards. At level 2, I would have at least 1 count against awards actor. And at level 3, 1 count at awards actor Daniel Day-Lewis. My UI would then take that and construct the tree out of those 3 different facet level values. This is actually a more generic mechanism for handling hierarchical data. So even within an application, if I wanted to search for things that had Daniel Day-Lewis in them with some award, I could search level 3 for awards actor Daniel Day-Lewis, and I would match all of the documents where Daniel Day-Lewis got an Best Actor award. So if your data has hierarchy in it, you build that hierarchy into your field structure and provide that at all of the different levels of the tree, and that gives you a lot of flexibility in terms of how to search against or facet and display facets against that data. I would point everybody at my reInvent talk this past year. I went into a lot more detail about this specific example. So if you need to see it visually, you can look for, I think it is Service FBC 302, and the video is up on the web.
All right. The next question is about integration options available with CloudSearch. Does CloudSearch work with an RDS database? Maybe use this opportunity to also talk about how you would source data, not just from RDS, but also other database options, Dynamo, Redshift, et cetera.
Sure. So as we looked at the initial view of the search document, we saw that there are different fields in there. There are titles, descriptions, actors, et cetera. A lot of that would come from originally a database. We also have scores and other data which is a little bit hotter. So if we have people who are rating or giving thumbs up or thumbs down, we want to have a very responsive store for that. Typically, Amazon DynamoDB is a good repository for that kind of information. And then we have even sort of cooler information like clips and reviews and information that's not changing very quickly but larger that may live in something like S3. So we have all of these different potential sources that we're going to construct into a single document. The way that you do that is essentially you write a script that would connect to these different data sources, pull information out of them, and then structure that information and put it into the content of the document. So at that level, we absolutely do work with RDS and DynamoDB and other data stores. There is that process that you have to build, the script, which is going to take your particular data set and structure it for search. We do have some integration with DynamoDB, as you saw in the upload documents. You can point the console at a particular DynamoDB domain. We also have a CLI that you can point at S3 or DynamoDB. This is a little bit more of a tighter integration with those services. And as we go forward, we're looking at how tightly can we couple CloudSearch so that you can have a more seamless experience to bring that data into CloudSearch without having to write a script yourself.
Okay, thanks for that, John. Next question, what exactly is the new text array type and when should it be used?
So as part of the update that we brought, we switched our back-end search capability. And the search engine that we're using now does differentiate between single value and multi-value fields. So the array types, we have a text array, we have a literal array, int array, double array, all of those are used for fields that have more than one value. There's a technical reason that we do that. In fact, single value fields can take advantage of some optimizations that let them work a little bit quicker, and the multi-value fields would be a little bit slower, but they allow you to put multiple values in them. So you'd use the array fields for multiple value fields.
Okay. Next question is again about language processing. If a collection has documents in multiple languages, how do you deal with language detection and appropriate text processing?
Yeah, it's an excellent question. We don't right now have automatic language detection built into CloudSearch. We do have a within our language processing, you can specify that a field, an individual field, has multiple languages in it. This would cause CloudSearch to process that field in a language neutral way, so mostly it will be tokenizing on white space. If your source documents have multiple languages, the usual way to handle that is to split them out into different fields and then process each of the fields according to the language of that field. So if you have, say, plot descriptions in English, in Spanish, in German, in whatever, you would have a field called plot_en or something like that, and you would configure CloudSearch to process that as English text. You'd have a plot ES, and that would be configured to process that as a Spanish field, plot DE, etc. So, and then the queries, as the queries are run, CloudSearch is aware of the configuration of the underlying field, so it will process the query differently for each of those potential matches. As the query goes against the Spanish field, the query will be processed as a Spanish query and go against that field. If you have location information in your application, you can also switch between matching the different fields based on what you know about the user, and you can put that in the query.
Okay, thanks, John. Well, we're almost out of time, so I'm going to take the last two questions here real quick, and then any questions we don't get to, we'll try to add it to our FAQ on the website so you can get the information you need. The one question is, can you tell us what the new search engine is, the one that you mentioned the CloudSearch switched to? I think the question is referring to the mention about Apache Solr. The latest version of CloudSearch now uses Apache Solr as the underlying text search engine. And the final question we'll take today is, which companies use Amazon CloudSearch? So we have several companies across the world using Amazon CloudSearch. Customers of CloudSearch vary in a variety of industries as well as company sizes themselves. We have a number of public references listed on our website. So if you want to take a look, if you go to aws.amazon.com and navigate to application services in Amazon CloudSearch, you'll be able to see all the public references we have, customers from a variety of industries and use cases.